Today I will be discussing the most interesting topic in the realm of software engineering, which is software testing. Specifically, I will be talking about the overview of software testing. I will define what software testing is. I will talk about the need behind software testing. I will also discuss about designing tests for high coverage and also practical aspects of unit testing, integration testing, system testing, and other types of testing will be discussed in detail. Let's start our discussion by raising a very interesting question. Do I need to do testing? So before answering this question, we need to know the meaning of testing or the definition behind software testing. Software testing is an integral part of software development lifecycle. So as you remember, in the software development lifecycle, requirement engineering is one, system design is another one, software development is another one. Software testing is also an integral part of this process. So from this end, the only question should be whether testing is conducted haphazardly by random trial and error or systematically with predefined plans. What it matters. The goal is to try as many critical input combinations as possible given the time and resource constraints. So the essence of testing is to try as many possible critical input combinations as possible, but considering the time and resource constraints. That means the goal here is to achieve as high coverage of the input space as is practical, while testing first the highest priorities combinations. But from this end, the main issue is that the strategies that you use to identify the highest priority tests. So identifying highest priority tests is also one of the challenge software testing engineers face in day-to-day activities or in daily basis. Now let's see the overview of software testing. So before we said software testing is an integral part of software development lifecycle. So it's the same as requirement engineering, system design, software development. But now let's formally define what software testing is. Software testing is a process of evaluating and verifying that software products or applications meet their intended requirements. So here we have two major keywords. The first one, evaluation or verification of the software or the product. The second one are target requirements or intended requirements. So the essence of software engineering is asserting whether the given product, a software product, is as per the intended requirements or as per the requirements given by the end user. So to this end, a software system that doesn't align with the actual requirements of the user might be called erroneous, but it's not really a good practice to say or to name these erroneous states as fault or defect or bug. So we shouldn't be using these terms interchangeably since they are distinct in their nature. So let's see the difference between these features. For instance, I would like to discuss with you the difference between four major types of errors in your software engineering testing process or software testing process in general. The first term we frequently use is defect. So defect doesn't mean failure or fault or error. Defect is basically a discrepancy between the expected and actual behavior of a software system. And the expected behavior of the software system is defined by the requirements which are specified in the requirement engineering phase. The second term that we use to interchangeably implement or take as is defect is fault. So fault is an incorrect step, process, or data definition in computer programs that causes the program to perform in an intended or unanticipated manner. The other important concept here is error. Error is basically a mistake made by human during the coding or testing process that can lead to a defect or fault. The other important concept here is bug. Bug is an informal term for a defect that has been identified and reported during the testing process. That being said, about the definition of software testing, there is one important concept that you have to know while working with software systems or while evaluating or verifying software testing. So, as it is clearly stated by Dijkstra, testing shows the presence, not the absence of bugs. Irrespective of the extent you have evaluated your system, you can only expose the presence of bugs. You cannot ensure absence of bugs. So this is the concept of complete testing. Other important concept, I would say, discipline under software engineering and specifically under software testing is test-driven development. Test-driven development is a software development methodology that mainly emphasizes writing tests before writing the actual code. For instance, as a classic software engineer, you might start by solving the problem. That means by writing a code to address identified problems in the requirement engineering phase. But a recent technique that has been implemented or explored by different software engineers is test-driven development. So this test-driven development is a methodology, a software development methodology that emphasizes more on writing tests before writing the actual code. So first you have to write tests based on the requirement, and in order to fit or address the requirements, the criteria of the test, you have to write the code. Okay, and it's an iterative process. So iteratively, you write test, you write an addressing code for that test, you see the result of your code by testing it again, and if the code has some issues, you refactor it. Okay, so this TDD or test driven development process typically involves the following iterative cycles. The first one is writing tests. That's why we say test driven development. The first step in the software development, if it is employing test driven development or TDD, is writing a test. So here developers start by writing a test that defines a small piece of functionality. After writing the test, you have to run the test. Okay? At this stage, you won't write any type of code to address the criteria of the test. You simply run the test. So for the first round, running the test yields failure, right? Because we will not have any code pertinent to the criteria of the test written. But iteratively, running tests might validate or verify the functionality of the intermediate code written for the previous test. After running the test, write code is the third step, in which you write the minimum amount of code necessary to make the test pass. Then after writing the code to address the test, already previously written tests, you again iteratively run all tests. And upon the result of this running of all tests, you refactor the code to address the problems identified or gaps identified in the existing code. And then you repeat this process from step 1 up to step 5 in order to come up with robust, reliable software system. So pertinent to this concept, test-driven development, there are major principles that we have to discuss. The first principle in TDD or test-driven development is red-green refactor cycle. This is basically a cycle of writing a failing test, which is named after red, writing the minimum code to make the test pass, it's represented as green, and then refactoring the code without changing its behavior. The second principle in test-driven software development is incremental development. You build the software incrementally, starting from a small piece at a time to a larger functional modules. Okay? Then the third principle in test-driven development is test automation. Here you have to automate the test and the process of validating or verifying, evaluating the functionalities of your code should be automated. So in general, automated tests are very crucial in test-driven development. They provide a safety net and allows developers to quickly run a suite of tests after each change to catch regressions. So that being said about the principles of test and the iterative process of test-driven development, it's also very crucial to highlight the benefits of TDD. The first benefit of TDD is improved code quality. Okay, you simply code on demand. That's the first benefit. The second benefit is early bug detection, because you write test, you evaluate your code, you write code for your test, you evaluate your code based on the previously written test, then you refactor it. This is an iterative process that lets you identify bugs at early stage of software development. Again, clearer requirements is the other benefit of test-driven development, because your tests are written based on the user requirements, so you will have the chance to refine the requirements of the user. And also it facilitates refactoring. It also enhances your documentation. This is a very important software development methodology which should be applied for non-trivial software development challenge or projects. So just to summarize, every step in the development process must start with a plan of how to verify that the results meet a goal. And the developer should not create a software artifact like system requirement, UML diagram, source code, unless that developer know how it will be tested. So everything in the test-driven development comes into existence if and only if it can be tested. So that being said about the test-driven development, now let's see the components of a test. So the major component of a test-driven development or software testing is a test case. So a test case is a particular choice of input data to be used in testing a program and the pair which is the expected output or the behavior of the system. So when we say a test case, it's a pair of input, critically identified input, and the expected output. So from this perspective or from this end, a test can be defined as a finite collection of test cases. Now I would like to give you some information about the two major strategies of software testing. The first strategy of software testing is called white box testing, and the second strategy is called black box testing. For instance, white box testing, it's also known as clear box testing or structural testing, or we also name it sometimes or call it sometimes glass box testing. The focus of this white box testing is the internal logic, code structure, and in general implementation details of the software that is being examined. Okay, white box testing is not that much interested in the input-output causality of your system on target or your system being tested. It's mainly interested or concerned about the internal logic, the code structure, the implementation details, or mainly the control flow, data flow in your component that is subject to testing. Okay, so the techniques that you use for white box testing could be, for instance, code coverage metrics based. When we say code coverage metrics based, it could be statement coverage based, branch coverage based, pass testing, or data flow testing could be used, or control flow testing could be one of the techniques that you employ for white box testing. The advantage of this white box testing is that the first thing, it provides thorough coverage of code bases because you focus mainly on the implementation details, so you get to know the internal logic of your system clearly. It also helps to identify logical errors, code security issues, performance bottlenecks in general. But when we see the setback of this kind of testing strategy, the first problem is that it requires programming skills. So any junior cannot do a very good white box testing. That's one of the setbacks. The second setback of this white box testing strategy is testing might be prone to bias by the tester's knowledge of the code. Okay, and also the desire to undertake complete testing is highly compromised in the case of white box testing. But when you come to the second strategy, black box testing, it basically explores input space of functionality defined by an interface specification. It mainly focuses on the behavioral aspects or functional aspects of your system rather than the implementation details of your system at hand. So here, in contrast to the white box testing, you might not need that much knowledge from the testers. So anyone who is familiar with software engineering could do software testing or black box testing. But the testing levels from the black box testing could be unit level, integration level, or components level, or package level. It could be system testing, or it could be also acceptance testing in the increasing order of its granularity. The techniques we implement for black box testing are many, but from them, for instance, equivalence partitioning or equivalence testing, boundary value analysis, decision table testing, and use case testing could be used. To say a little about the advantages and the setbacks, disadvantages of black box testing, the first advantage of black box testing is that testers do not need programming knowledge, and tests are based on user requirements and expectations because it's more to evaluating the behavioral aspects of your component or system or unit under test. The disadvantage of this type of testing strategy, is that the first, it will have limited coverage of code paths because it doesn't care much about the implementation details, the control flow, or data flow of the component under test. The second disadvantage would be it might not identify certain types of errors like logical errors in the code. Now, let's talk about the reason behind the complexness of or the hardness of software testing. So, to give you some context, any non-trivial system, any significant system cannot be completely tested. That is one of the main challenges in software testing. For instance, assume the use case one of the smart home system that we have been discussing in the previous lecture series. The unlock system has different alternatives, as we have seen in the sequence diagram or in the scenario compartment of the use case diagram. So all those combinations should be tested during the phase of software testing. So most of the time, if you have non-trivial system, that means a very significant system or a system that resembles the real world complexity, then complete testing is not possible. So because of this, software testing is very, very hard. The other thing is that our goal is to find faults as cheaply and quickly as possible. So ideally, we would design a single write test case to expose each fault and run it. But in contrary, or in practice, we have to run many unsuccessful test cases. When we say unsuccessful, which are test cases that cannot or will not identify faults. So before coming up with a successful or critical test case, we have to run many unsuccessful tests that do not expose any faults. So here we do have another trade-off in software testing, the trade-off between test coverage and economy. Okay, the idea behind software testing is to have high degree of test coverage, but by keeping or preserving the economic constraints or the cost constraints. So usually cost is, or economic aspects, from the economic aspect, usually resources are limited, time is limited. So we can define this one from the economic perspective. So within this constrained environment, limited environment, a software engineer or software test engineer should strive or thrive to come up with a high degree of test coverage. So this is a big trade-off that you have to balance while doing software testing. The other one is that the underlying idea of software testing. So the correct behavior on critical test cases is representative of the correct behavior of untested parts of the state space. That means if you test 10% of your system, so you assume those 10% of test cases and the behavior that you saw in reaction to those 10% is the representative of the overall behavior of your system. So this is, very generic induction process that might end up, or that might push you to end up with wrong conclusion. Now let's talk about the logical organization of testing. I would say the different levels of testing. Software testing is organized logically in this manner. First, you have unit tests, and then there is integration test that tests various unit tested components, and then we have system test, overall generic test, and then we have different types of system tests or varieties of black box tests. Okay, so this diagram basically describes the logical organization of testing in all-inclusive manner. So here, for instance, in this manner, you see the degree or the level of test components being tested is in the order of ascending. That means the smallest unit is here, which is under unit testing. The collection of units is subject for integration testing, and the collection of components or subsystems is subject for system testing. Okay, together. And finally, we do have two kinds of strategies, test strategies. White box testing is usually done by the developer, and there is another testing strategy which is black box testing, and customers are responsible most of the time to undertake this black box testing. And black box testing is more to system testing and acceptance testing, but white box testing is more to unit testing and integration testing. So before diving more about, the remaining topics of this chapter, let me address each of these levels of testing one by one. Let me start with unit testing, for instance. So the purpose of unit testing is to verify that each unit of the software performs as designed. So what do we mean by unit? So if you are applying object-oriented software design methodology, then unit could be instance methods. Okay? Unit could be instance methods. In some cases, units could be classes. A single class could be a single unit. Okay? So the scope of this unit testing is the individual components or functions in your system or methods in your system. So the tools that you could use to test your units in a given software environment are, for instance, JUnit, NUnit, or different testing libraries depending on your programming language. The second level of software testing is integration testing, as it is seen here in the middle. The purpose of integration testing is to identify issues related to the interfaces and interactions between integrated components. So the scope of this integration testing is testing the interactions between integrated components or systems in some cases. Okay, so there are different types of integration testing, like top-down testing, bottom-up testing, or incremental integration testing. So you could use different tools to undertake integration testing, like mock objects or tools that simulate external systems. The other most commonly employed type of or level of testing is system testing. This system testing has a scope of an entire system. Okay, the whole system is subject for system testing, and the purpose of this system testing is to verify whether the software meets the specified requirements and functions as intended. For instance, the types of system testing are functional testing, performance testing, security testing, and any other testing types could be mentioned here. Okay. Now let me extend our discussion to other types of testing which are similar to system testing in some perspective. For instance, acceptance testing, as you can see here. So acceptance testing is a type of system testing. Okay, it evaluates whether the software satisfies business requirements or not. So its purpose is to ensure whether the software is acceptable for delivery to end users or customers. So user acceptance testing, for instance, UAT, alpha testing, beta testing are some of the types of acceptance testing. So you could use different tools, or also, usually we use manual testing mechanisms, test scripts, or tools like Selenium are used to perform automated acceptance testing. Another interesting testing, which is not really mentioned in your slide, is regression testing. So the scope of regression testing is to ensure that recent changes to the code haven't adversely affected the existing features. So its purpose is to catch regressions, bugs, or unintended consequences introduced by code changes. So for this, we could use tools like automated testing tools, test suites, or continuous integration systems like Jenkins. Performance testing is also among the types of testing that could be defined in the realm of the logical organization of software testing. In case of performance testing, you evaluate the software's responsiveness, speed, stability under different conditions. So the purpose of this one is basically to identify performance bottlenecks, ensure scalability, or optimize resource utilization. So load testing could be one, stress testing could be another, scalability testing is also a very important one. For instance, JMeter, Apache JMeter, Load Runner could be used as a performance testing tool. Another testing that we have discussed in the previous or in the early stage of this lecture is security testing. The scope of security testing is to identify vulnerabilities or weakness in the software security, and its purpose is to ensure whether software is resistant to unauthorized access, attacks, or data breaches. For instance, penetration testing, vulnerability test scanning, security audits could be implemented as a security testing. But by the way, this security testing is another separate big testing realm. So in our country, for instance, organizations like INSA are responsible to undertake such kind of tests, in general. But it's not specific to, penetration testing or vulnerability testing or security audit, but there are variety of cybersecurity um, principles. So they usually implement or employ techniques, security testing techniques, in adherence to the principles they listed. The other very user-friendly testing type is usability testing. So this is mainly to assess the software's user interface and overall user experience. The purpose of this usability testing is to ensure whether the software is user-friendly and meets user expectations. Okay, you can achieve this type of testings by like user interviews, surveys, or also you can conduct usability testing sessions. Okay, so for instance, feedback collection tools could be used for this one. Usability testing tools can also be used in this scenario. Another testing, for instance, quality testing, which is mentioned here, it verifies non-functional requirements, and in contrast, function testing verifies the functional requirements which are listed during the requirement engineering phase. Okay. Another different testing type is installation testing or deployment testing. It tests in user environment platform whether the system works as expected in the user environment or not. We have already discussed about white box testing and black box testing as a strategies of testing, and also unit testing is also clearly discussed, and also integration testing were also elaborated. Now let's talk about acceptance tests. And let's take an example from the previous scenario, which is for the system safe home access system. And specifically, let's focus on the use case one, which is a use case for unlock. So you have to recall what we have done in the requirement engineering phase, or what we have learned in the requirement engineering phase. There we said requirement one generated use case one, which is use case unlock. So we can generate different acceptance test cases. For instance, the first acceptance test case could specify, uh, to test your door with the valid key of a current tenant on his or her apartment. So the test or pass criteria for this would be pass. That means you are testing whether the system responds positively for the correct tenant and for the correct valid key, for the correct key. Then the pass-fail criteria that you put for this test case should be pass. So the expected result is a pass-fail criteria, okay? The other test case could be, for instance, to test with the valid key of a current tenant on someone else's apartment. So the pass-fail criteria for this one should be fail, because the person has the right, the valid key of a current tenant, but he's or she's applying that valid key on different apartments, so it should fail, right? The other test case, for instance, test with an invalid key on any apartment, so the expected result the system should fail. Okay, the system should fail, or the person should fail actually, rather than the system. The other test that you could write under the umbrella of acceptance test is test with the key of a removed tenant on his or her previous apartment. So, for instance, if a tenant is removed from his apartment, then his key should not work on that apartment. So this test case verifies whether the system handles this or not. So the pass-fail criteria tells what the system should respond, for instance, or how the system should react to this action. So, for instance, if the user tests the system with a key which is a key of removed tenant, the user should reject this scenario, right? So for that purpose, the pass-fail criteria will be failed. That means the system should make the user to fail from its desired goal. The last, sample that is used to show how acceptance tests could be written is test with the valid key of a just added tenant on his her apartment. For instance, if you just enroll a new tenant to your apartment, then the key that you provide to that tenant should be operational. So you write test cases by considering such kind of scenarios, and as you remember, this kind of scenarios could be extracted from the dynamic model. Now let's see an example for test case use case correlation. Let's use the previous use case one, which is a use case for unlock in the case of smart home system. And let's derive a single test case identifier or test case for that specific use case. This specific use case could have more than one test cases, but here we are using only one possibility or possibility of generating use case in the case of unlock use case. So a typical test case would have test case identifier that lets you identify the specific test case from other types of test cases defined on this specific use case. And it has correlation statement to correlate it with the use case, the target use case. We call it use case tested. And under use case tested, use cases which are going to be addressed through this test case are listed. For instance, here, use case main success scenario and use case 7, use case 1 and use case 7 are addressed. The other important thing that you have to include inside your test case specification is a pass-fail criteria. So the test passes if the user enters a key that is contained in the database, in the case of use case 1, and including the constraint with less than a maximum allowed number of successful attempts. So some test case passes if the user enters the right key, and if the number of attempts the user uh, used is less than the maximum one, then we call that test case it's a pass criteria, and it fails unless this condition is fulfilled. The other important thing is data, input data, the data that the use case takes. In case of use case 1, smart home access unlock use case, we use numeric key codes and a door identifier, so we can consider this as input data. The other component in your test case is test procedure. This explicitly specifies how you undertake or undergo testing. So in the case of use case 1 and test case 1, the first step is set to be type in an incorrect key code and a valid door identifier. The second step is type in the correct key code and door identifier. So in the first scenario, for instance, in step 1, you input incorrect key code on the right door, okay? In the second scenario, you input correct key code and door identifier. So in the second case, the system should pass. In the first case, the system should fail. So in the case of first one, expected result is system beeps to indicate failure because there is incorrect key code, and records unsuccessful attempt in the database. For instance, if the number of unsuccessful attempt is 1, then upon each failure, the system will increment the unsuccessful attempts number by 1, and then it prompts the user to try again. So this is the expected result from the system in case of test case 1. Whenever you insert incorrect key code on the valid identifier, on the valid door identifier, it should beep to indicate failure. That's the first thing. It should also record unsuccessful attempt in the database, and then it should prompt the user to try again, unless the number of unsuccessful attempts are more than or greater than the maximum possible number of attempts. In the second case, everything is fine. The input data is fine. The door is the right door. Then the expected result from the system is system flashes a green light. Green light is a good light to indicate success. Then record successful access in the database, and it disarms the lock device. So this lock device will consequently light up the room and also open the door and everything required when a person enters to his or her house. So this is a typical specification for a simple test case, okay? So in this test case, we tried 2 scenarios. One with the correct key codes. The second one is with incorrect key code. Or the first case, step 1, is with incorrect key code and a valid door identifier. And step 2, type correct key code and correct door identifier. And the corresponding expected results are also set here. So this is how you simply classify one function as valid or verified or unverified, okay? If something passes through the correct inputs, if some function passes through the correct inputs and fails through incorrect inputs, fails in a sense, if the system correctly identifies the incorrectness of inputs, then we label that function or component or unit as a correct unit, okay? But if the system works, for instance, in the case of incorrect key code, like if the system opens the door in the case of incorrect key code and incorrect door identifier, or in any of these 2 cases, then the system in general, the test fails. So we have to refactor the system so that we can fit it to the test case expectations. So another important concept while talking about software testing is test coverage. So in the previous session of this lecture, we discussed about the impossibility of complete testing. So we need to have a measure, a metrics to evaluate the correctness, like the degree of coverage of tests, okay? So we can first define the test coverage, and then we will see the 2 perspectives of test case coverage. So test coverage generally measures the degree to which the specification or code of a software program has been exercised by tests. We can define the degree of test coverage by considering input coverage, input space coverage, simply by looking at the amount of input that we had and the amount of input that we have used during the testing phase. This is the first one. So it's a specification testing in general. The second approach is a code coverage code coverage based test coverage. This basically really doesn't concern or doesn't worry much about the amount of input data utilized, but it mainly focus on the degree to which the elements of the program source code have been tested. So in the case of the first specification testing, we can mention one good example like acceptance tests, which mainly focus on covering the amount of input space or the like covering the input spaces that we have elicited. But when we come to code coverage based test coverage criteria, general unit tests could be mentioned here, because here in case of unit tests we usually focus on implementation details and the amount of elements that our program or our test cases addressed are used to define the degree of test coverage in general. So to this end, it's better to discuss about the heuristic for software testing. When we talk about heuristic for software testing, these are, we can identify them as or define them as techniques or functions that lets us, compute or identify test cases which are effective to the domain and in a very small amount of effort relatively. So from this perspective, for instance, some tests are or techniques are more critical than others, or some test cases are very important, some test cases are irrelevant, and the way to come up with relevant test cases can be referred to as heuristic software testing. So in case of heuristic software testing, generally test cases should be prioritized. This is mainly due to the fact that some tests are more likely to uncover faults. So those tests which are more likely to uncover faults should be deprioritized. The second thing is that tests are about finding developer errors, and people are prone to make certain kinds of errors. So for this purpose, we have to use some heuristic approach to come up with relevant tests. So to this end, we can classify heuristic approach for software testing under the strategy of black box testing and white box testing. In the case of black box testing, it's basically a behaviorist testing approach in which input data is fed to a black box unit, and this black box unit is evaluated based on the output it generates. So this is basically input-output testing. So in this category, we can mention two heuristic testing techniques: equivalence testing and boundary testing, which lets us identify inputs which are more relevant to the thing that we are going to achieve. From the white box testing perspective, in the previous class we have discussed about what white box is. So white box is mainly a testing mechanism that focus on implementation details, control flows, data flows, rather than input-output, okay? So under this category, we can mention two more heuristic approach. The first one is control flow testing, and the second one is state-based testing. And then in the next few slides, I will be discussing about the essence behind this heuristic approach. So the first category that we have used to classify test coverage were input space coverage, and the second was code coverage criteria. So under the input space coverage criteria, which is a black box based testing technique, in this, the first one is equivalence testing. So as I have already mentioned, this equivalent testing is a black box testing method that mainly divides the space of all possible inputs into equivalence groups, such that the program is expected to behave the same on each input from the same group. Look, for instance, you may have to feed your component or the unit under test some sort of inputs. For instance, the valid size or range of inputs that your unit under test has to accept is, say, from 0 to 100. Okay, So equivalence testing is basically about equally partitioning this range of values from 0 to 100 and identifying, model inputs from each of them, or sampling inputs from each of them so that they can be tested, or the result that we get from each category of inputs reflects or resembles the result we might get from the same group. Okay, so the assumption here is that a well-intentioned developer may have made mistakes that affect a whole class of input values, and we do not have any reason to believe that the developer intentionally programmed special behavior for any input combinations that belong to a single class of input values. So taking this into account, taking the fact that developer won't program or won't modify or mutate the program to act one way for some input groups and to act another way for some other input groups, then we assume that equivalent testing criteria or heuristic approach gives us a candidate inputs from each of those partitioned groups, and those partitions should be equally splitted. Okay, for instance, if you have, as I already said, if you have a valid input set from 0 up to 100, then you might have to define your equivalent testing criteria with the offset of 10 values, 10 digits, okay, or 10 numbers. For instance, from 0 to 9, then 10 to some 20, 20 to 30, like that, okay? And from each of these partitions, you have to select to the maximum of, one or some number of candidates or samples. Then you execute your tests based on those samples and conclude that or deduct that the behavior of the system on all input sets will be the same. Okay, so it's a two-step process. The first one is partitioning the value of input parameters into equivalent groups, and the second step is choosing the test input values from each group. So here, as you can see, for instance, we assume this 0 up to 100 is a valid equivalence class, and in each of these we might have some partitions, classes. We might have, for instance, we may say we have 10 classes, valid equivalence classes here. So from each of these, the first thing is, as I already said, partitioning the values. So this is the first step, partitioning the valid equivalence classes, or partitioning the whole range so that you can get the valid equivalence class. And the second step is choosing the test input values from each group. Okay, from here, you have to choose the test input values. So it's not necessarily, important to partition only the valid equivalence classes, but in most cases you have also the mandate to partition or create invalid equivalence classes. Invalid equivalence classes are classes or set of inputs that should not be fed to the system, but for the case of evaluation and testing you need those kind of inputs, so you also have to partition those invalid equivalence classes. Okay, this is how the equivalence testing input space coverage based testing criteria works. So regarding finding the equivalence classes or the heuristics behind it, it's better to take these general guidelines or principles. We can take these guidelines or principles as the heuristics for finding equivalence classes. The first one, for an input parameter specified over a range of values, example, it could be a number or letter or partition of, partition of any other sequential information, then the rule would be to partition the value space into one valid and two invalid equivalence classes. Okay, so for an input parameter you have to come up with one valid class and two invalid equivalence classes. Okay, in the case of the previous example, for instance, you may have to come up with one valid equivalence class, okay, and two valid, like this is a valid equivalence class one, and this here is another invalid equivalence class. Here to the left is another invalid equivalence class. So for one valid equivalence class, you have to come up with how many? Two invalid equivalence classes. The second case, for an input parameter specified with a single value, example could be a Unix security key code, then the rule or the heuristic would be to partition the value space into one valid and two invalid equivalence classes. It's more or less the same as the previous heuristic. For the third one, for an input parameter specified with a set of values, could be, for instance, day or men's, names of men's. Then the rule would be to partition the value space into one valid and one invalid equivalence classes. And finally, if you have Boolean values, then you are recommended to partition the value space into one valid and one invalid equivalence class. So this is basically the heuristics for finding equivalence classes. So those valid equivalence classes are classes that contains input sets which are allowed to be applied on the system or the unit under test. Whereas the invalid equivalence class constitutes inputs or data, input data in general, that is not or that should not be fed to the system. So the system always should respond with negative answers for each and every of invalid equivalence class members. The second heuristic testing approach or heuristic approach, or generally software testing approach, which is a black box testing approach, is a boundary testing approach. So it's a kind of equivalence testing approach, but it has some special cases. So that special case is that it mainly focuses on the boundary values of input parameters. Rather than partitioning the whole input space into equivalent classes, it mainly focuses on the boundary aspects of input values. Again, those equivalence testing techniques and boundary testing techniques are mainly input space coverage based techniques. But equivalence testing technique mainly focus on partitioning the input space into equivalent classes. But boundary testing technique is kind of equivalence testing technique, but it mainly focus on the boundary values. For instance, in the case of equivalence testing, we have boundary values 0 and 100, right? So if you are interested to exploit inputs around the boundary, that means in between the valid and invalid equivalence classes, then that will be boundary testing or heuristic approach. And it's mainly based on the assumptions that developers often overlook special cases at the boundary of equivalence classes. This is mainly, or this can be mainly elaborated by using the example that we have heard in the case of Microsoft Zoom bug. So this is a very popular bug that Microsoft had come across at some point in time. So this application, the Microsoft Zoom, was not set to understand the concept of leap year. So on that day, on the leap year day, the Microsoft Zoom was not able to identify the way it should have used to change from one day to the next date. So that was a big issue in the realm of consumer electronics at that time. Then Microsoft was able to fix this issue by refactoring the software somewhat, but this was registered as one of the bigger failures due to lack of testing techniques, specifically boundary testing techniques. So the leap year was at the boundary of the men's input set or input space, and they were not able to consider this while developing the Zoom application. So that caused a lot of problems at that time, but Microsoft has solved it, and it's. I really recommend you to read about this bug, how they solved it. How is it related to the boundary testing? So it's very beneficial. The principle here is that select elements from the edge of each equivalence class or outliers. Okay, so this is how you relate equivalence class with boundary testing. Okay, for instance, in the case of equivalence class, you might be interested to select at the outliers of the input space, or even you might be interested at the boundary objects or inputs between two consecutive equivalence classes. Okay, in this case, the type of test you are undertaking is called boundary testing, or the heuristic is boundary based heuristic. Okay. So, for instance, when we say outliers or edge of equivalence class, it could be, for instance, 0 or the minimum or maximum values. It could be empty set, for instance. This could be considered as an outlier. Empty string, null. Null should be specifically considered because of its weird representation in the case of persistence models. Whenever you represent null in your database, then it cannot be computed as you compute numbers, literals, or any other data. Null is not equal to null generally. So this is a major problem. So you have to check for such kind of outliers, and it can be only tested by using boundary tests. And also it should be an issue to compare or to resolve issues related to greater than or equal to some kind of, different but things that look equivocal. Okay, for instance, palindromes. These are kind of computer science problems for which you cannot derive finite state machines. Okay, so such kind of outliers and edges of equivalence classes should be considered during boundary testing. That being said, about black box based heuristic approach, the next would be code coverage based or implementation detail based or white box testing approach or heuristics based on the white box principle or strategy. So the first type of code coverage based testing is control flow testing. So a given unit, or it could be a given component or subsystem or system, has this entity or token called control. So a control can be at exactly one point at a time. So you cannot have, in a given system, you cannot have multiple controls dispersed over the system domain at a time. So whenever you are concerned with one execution of your execution of your software, then control will be at one point at a time. So it cannot be anywhere else at a time. Okay, so for that purpose, you tend to evaluate the functionality of your unit under test by tracking and validating the correctness of flow of that control or that token. Okay, so different types of control flow testing are there, among which the most important ones are statement coverage, edge coverage, condition coverage, and pass coverage criteria. So when we say statement coverage, basically it's executed, with the intention of handling or addressing each statement at least once by some test case. Okay, each statement, for instance, a plus b is equal to c. If there is such kind of statement, then that statement should be addressed at least by one test case from the whole set of statements. Okay, so a control flow testing, the first type is generated or developed with the intention of achieving a total statement coverage. The second one is edge coverage or branch coverage control flow testing. So in this case, every branch, every edge of the control flow is traversed at least once by some test case. A slightly different one from the first and the second control flow testing strategies is condition coverage. So whenever we have expressions that evaluates to true or false, we call them conditions. So condition coverage control flow testing generates test cases that addresses each conditions in your unit at least once. In the case of not only once, but in the case of true, in the scenario of true, that means in the scenario where this condition is evaluated to true, there should be one test case, and there should be another test case or a pass, that takes care of a situation or a scenario where a unit evaluates to, or the condition evaluates to false. Okay, so every condition takes true and false outcomes at least once in some test cases. So this is called condition coverage criteria. The last control flow testing type is pass coverage criteria. So whenever we say pass, it's a sequence of nodes in your unit from initial state to the goal state. The goal state is whenever the program returns some input for the caller. So pass coverage criteria is basically about covering all passes that leads you from initial state to the goal state. Okay, so it basically finds the number of distinct passes. So distinction is very important because you shouldn't be covering a single pass twice. So it's about basically finding the number of distinct passes through the program to be traversed at least once. So constructing the control flow graph of a program, for instance, for edge coverage looks like this one. Okay, so here we have some conditional statements, for instance. Here we have simple statements or branches, for instance. So for all of them, control flow graph can be drawn like this. So I recommend you basically to refer back to your book, which gives you very depth understanding of these techniques, how to draw control flow testing, how to draw data flow testing, how to draw state space or state diagram in general. So that's very important. So just read your book for further information. So the other code coverage criteria is state-based testing. Okay, so here you design a state diagram in general. So state-based testing defines a set of abstract states that a software unit can take and test the unit's behavior by comparing its actual states to the expected state. Okay, so state is basically kind of abstracting. Okay, for instance, at a time, an object could have some set of values, so that describes its state. Okay, for instance, it could be, a set of values for your attributes, or we can also generally define a state as a constraint. Okay, a constraint on the values of its attributes or objects' attributes. So for this specific purpose, for the fact that state-based testing is applied on objects that has or that have attributes and values which are a constraint for the attributes, then state-based testing is mainly applicable for object-oriented systems. So the reason that we say the state of an object is a constraint or applied on attributes is that the state of an object is mainly defined by its attributes at the class level, but at the object level, whenever you instantiate your classes to as object, then the general specification given for the class is constrained by the values that you give to the attributes of that class during the phase of object instantiation. So this is mainly related to the object-oriented systems. So because of the methods, because the methods use the attributes in computing the object's behavior, the behavior depends on the object state in general. Okay, so one different concept here is that an object without attributes might not have a state, but it can still be unit tested. Okay, it can still be unit tested by its default constructor. Some examples for state-based testing. So as you remember, state is generally an abstract entity. So for safe home access system, for instance, we can define the following states. So just you could have multiple states, like numerous states for your unit, but the most relevant ones should be identified based on some heuristic. For instance, in the case of locked states, for instance, for smart home access system, locked state can be defined as this expression: locked device armed is equal to true and number of attempts is equal to 0. This defines what locked state is in your system. So whenever you find or whenever you come across a state that evaluates to true for these expressions, then you can define it as a locked state. The other state is, for instance, accepting state. You can define accepting state by the logical end of locked device armed is equal to true and 0 less than or equal to number of attempts less than or equal to maximum number of attempts. The same goes for all states that you identify from your unit or your system in general. But the general principle here is that define the relevant events. Okay, defining the relevant events. So from this perspective, the relevant event would be a user enter, a valid key, user enter, an invalid key. These are events, right? From those events, you may happen to identify important states. So this is a sample state-based testing or state graph in general. So here we do have states, locked state, unlocked state, accepting state, and blocked states. And here in between each state there are transition functions in general, or data that contributes to transition from one state to another state. So here, as I already said, it's transition. Here is a state. So in the case of every transition, we will have corresponding input data. For instance, to transition from locked state to unlocked state, we need a valid key, right? Or we need a signal success for the device control to unlock the door. To transition from locked state to accepting state, for instance, your system needs to face an invalid key or a signal failure. Okay, so in the accepting state, you might try to check another input from the user. So in each loop, the user might create or feed invalid data. So an invalid event state will be raised. So signal might fail, you know, and this can be further described as this state. Like accepting state is number of attempts less than maximum number of attempts in general. Okay. So to transition for a state to transition from accepting state to blocked state, it needs an invalid key, and the number of attempts should exceed the maximum number of attempts allowed, and the result would be sound alarm. So this is a generic state graph that shows how events are created and how those events lead to the creation of states, and what kind of inputs generates or leads to what type of state. Okay, and what will be the consequence of some input on some state. For instance, the consequence of invalid key on accepting state could be a sound alarm. Okay, so this is clearly defined by state diagrams. Okay, state diagrams. So from the previous example, the diagram elements, the controller state diagram elements are, for instance, constituted of 4 states like locked, unlocked, accepting, and blocked. We do have 2 events, the valid key event and invalid key event. And also we have around 5 valid transitions from locked to unlocked, from locked to accepting, from accepting to accepting. Look, from locked to unlocked, 1 transition, from locked to accepting, from accepting to accepting, okay, from accepting to blocked. These are, and from accepting to unlocked. These are the 5 transitions our state diagram depicted. So state coverage are ensured based on the following conditions. The first one, cover all identified state at least once. So each state, for instance, locked, unlocked, accepting, these states should be covered at least once by one test case. So this is one of the conditions to ensure the complete state coverage. The second one, cover all valid transitions at least once. Those valid transitions, are locked to unlocked, locked to accepting in the case of the previous example. And the third one is trigger all invalid transitions at least once. Let's talk about the practical aspects of unit testing. So when you execute tests in reality, in practice, there are things that you have to consider or use in general. So we call the most important components that you use while unit testing in the practical domain mock objects. So there are 2 types of mock objects. The first one is a test driver, and the second one is a test stub. So basically, a test driver simulates the part of the system that invokes operations on the tested component. So if there are hosts from or hosts that gets information or data or service from the current unit under test, you call those type of units test drivers. Mind you, these are mock objects. They are not real objects. So whenever you want to test your system or your unit, any unit, you have to consider operations or another units that are using this unit, and you have to simulate them as a test driver. The second case would be units that are being used or will be used by the unit under test. We call them a test stub. So for a software test engineer to evaluate or verify the functionality of a unit, first he or she has to simulate the test driver and a test stub, or he or she has to simulate operations that are using services of the unit under test as a test driver, and operations this unit under test will be using as a test stub. Okay, so the reason behind mock objects, to use mock objects or this simulation, is that the corresponding actual objects are not or will not be available during test. Okay, since we are undergoing unit test, And the other simpler reason would be it's easier to locate faults using mock objects that are trivial and therefore not a source of faults. So the unit to be tested is also known as the fixture. This might have a slightly different meaning when you come to the framework JUnit, because in JUnit we use the term fixture to represent data that will be used by many test cases, okay? But generally, the unit under test here in theoretical aspect is referred to as a fixture. So generally, testing is all about generating the fixtures, test drivers, and test stubs. So the procedure or the cycle of testing or unit testing in generally starts by creating the thing to be tested, which is fixture, then the driver, then the stubs, and then in the second step, we have the test driver invoke an operation on the fixture, and the third step, we evaluate that the actual state equals the expected state. This is a very good example to show what is a test driver and what is the test stub. So in the case of, for instance, the checker sequence diagram that we have been discussing before under the use case one and the sequence diagram that belongs to use case one, which is unlock use case, the dynamic model is put in the left side. So here we have a controller, a key, checker, and a key storage. Okay, so these are objects that the unlock use case uses to operate. So these are the details. I won't be talking about the details, but I will be focusing on these objects because we are going to test these objects separately. So assume the test case is targeting this checker. Okay, so in case of this checker is mainly triggered by the controller. Okay, the operations of the checker are said to be used by the controller, and the checker uses the key here to check, and against this key storage or persistent model. So from this example, the test driver is the controller, the fixture is the checker, and these two are test stubs. That means the checker will be using the key and the key storage to check the validity of the key provided by the controller or the test driver. So this is how you formulate test drivers, test stubs, and fixtures, or a component to be tested. A typical example for a test case for key checker looks like this one. This is a Java code. So it defines a class checker test, and it defines a test method with a notation test, which has a public access modifier and return type is void. So it has a name, check key, any state, invalid key, rejected. So any test case or any software testing should follow these three major steps. The first one is setup, the second one is act, and the third one is verify. In the setup phase, as we have already discussed before, we, instantiate objects basically. So we instantiate a checker object with the name or identifier fixture with new checker. Okay, so here we use generic constructor parameters if we have there. Then once you set up the component to be tested, which is the checker, by the name of fixture, the second step would be to act. Basically, acting means simply evaluating the function, okay? Or just not evaluating the function, but executing the function. So according to this fixture, here we have a fixture, for instance. Then here we have a key. This is basically a test stub. So we instantiated a key with some invalid code, for instance. For this purpose, we need to feed the system an invalid code, okay? And once we instantiate the invalid code class by invalid test key object, then we feed this key to the Boolean type result, and fixture is evaluated by the invalid key, and the evaluator for the checker class, the evaluator function or method is check key. So fixture.check key accepts an argument invalid test key, which is this one here, and the result is finally asserted by the verification phase. So we simply asserted by assert equal in this case, for instance, and we are asserting the similarity or the equality between the result that we get after executing and the expected output. So in case of invalid code, the check key of a checker class, the check key method of a checker class should return false or wrong key message. So here we are verifying the correctness of the function by asserting whether the function returns false or not. So these are basically the three major phases of unit testing: setup phase, act phase. So in the setup phase, we are simply instantiating the fixture, or the component to be tested. In the act phase, we instantiate all the test stubs, okay, all the test stubs and test drivers, and execute the program under test and store the result. And in the final stage, which is the verify stage, we assert the reliability of your unit according to the expected result. So just to summarize this, test case should be named by generally considering the three phases of software testing, unit testing. The first name of your test case should belong to the action. For instance, it could be the method name. The middle name of your test case should be, reflecting the setup phase, and the last or the postfix of your test case name or method name should reflect the verification phase. For instance, if you see the name of this test case, which is check key any state invalid key rejected, which directly belongs to the action method, the setup, that means basically the starting state basically, and the verification phase belongs to the expected result. So here the verification phase is invalid key rejected, okay. The state phase here, the action phase, is any state, and the first phase would be the check key, the method under test, which is. So we could use different frameworks for testing. We could use XUnit, JUnit, NUnit, could be used for unit testing, okay? So verification of the expected result is usually done using the assert method. This assert could be assert equals, assert null, assert true, assert anything, okay? According to the limits given by the frameworks, the testing framework, XUnit, JUnit. So basically we use assert methods to assert the equality or the similarity between two objects, okay? Between two objects. So for instance, in the case of assert true, this simply takes some inputs and or some expressions and make sure the evaluation that we get, or the results that we get after evaluating this, is the same as this one, true. Okay, it's assert true. So whenever the output for this expression is true, then the assert true returns true, otherwise it will return false. Assert equals is kind of a binary method which takes two inputs. The first one is the expected input and output, and the second one is the actual output. The actual output is gained after the act phase of unit testing. Assert null is also a unary operator that simply checks whether an object or any entity which is fed to it is null or not. So far we have discussed about unit testing, in which single units or components are tested or verified. Now let's talk about integration testing, which is a way to assemble individually tested units and quickly locate faults that surface during integration. So that's why we call it integration testing. So a test that exploits issues or faults caused during integration or for the main reason of integration or interaction. So there are different dimensions or tabs to classify or define integration testing. We can mainly define or classify integration testing techniques as horizontal integration technique or vertical integration technique. The most widely used horizontal integration techniques are Big Bang integration, bottom-up integration, top-down integration, and sandwich integration. We will be discussing about the essence of each of these integration techniques in detail. But to give you some insight, Big Bang integration technique is a way to exhaustively combine all individually unit-tested components and see whether it works or not for some sort of test cases. Okay, so in this kind of test cases, it's the main challenge, is it's hard to isolate individual units that cause the integration testing fail. So you might get some faults, but you cannot simply locate the source of those faults, since you are testing the system exhaustively and in a big bang approach, aggressively. The other compartment, or dimension to classify integration testing is vertical integration technique. It's mainly a user story based technique. It simply slices the system vertically, uh, by using use cases or user stories, and then first integrate within each slice using any horizontal integration technique. So vertical integration technique is basically a slice and horizontal integration approach. Okay, it slices the overall system by use cases and then applies horizontal integration techniques. Could be bottom up, top down, or sandwich, or for that matter, it could be big bang integration. So horizontal integration testing here is depicted in 3 different modalities. The first one is system hierarchy. Okay, so depending on the hierarchy of components in your system, you can incrementally test the integration between unit tested or individually tested units. In the second case, we have bottom-up integration testing. The bottom-up integration starts from the lower units, the smallest units, individually tested units, and gradually combines or integrates those units, leading you to the system level testing or subsystem level testing. The advantage of this bottom-up integration testing is that only few mock objects or like only few test stubs and drivers are needed to be implemented. But the drawbacks for this kind of integration testing is that end users cannot see any functionality until the late phase of the development process, software development process or testing process, because you are starting from the smallest units and gradually you might see the big picture of your system, but at the early stage of this testing, the users might not be able to see the big picture or the functionality of the system as a whole, since the subsystem level functionality of the system is manifested, or it manifests at the middle stage of the testing process, and the overall functionality of the system manifests at the end of this bottom-up integration testing. So to this end, to the bottom-up integration testing end, we have come up with a new testing approach, which is top-down integration testing approach. It starts from the big picture of the big entity, most of the time the controller of the units under test. Okay, so basically from this diagram, the top-down integration test starts from level 4, and which is the controller, and gradually integrates all the tiny components up to the leaf nodes or the individually tested nodes in the hierarchy. When we come to vertical integration testing, if you consider this as a whole subsystem, then the whole subsystem will be dissected or splitted into different or unique, distinct user stories, and horizontal integration will be applied for each of these stories in general. So it's also possible to define or elaborate vertical integration testing as a combination of unit testing and acceptance testing. So here in this diagram, we do have an inner feedback loop for unit testing and an outer loop for acceptance testing. So vertical integration testing is all about writing a failing test unit test. You may start from writing a failing acceptance test. Then in the inner loop, you write a failing unit test, then make the test pass by, refactor it, then iterate through the inner loop until you get a unit that passes through all tests. Then once you have tested everything under unit level by using the inner feedback, then you feed it to the outer feedback loop, which again writes a failing acceptance test. And for every failing acceptance test, you have to write a failing unit test. So this is very clear cycle of unit testing and acceptance testing. So the test stops whenever you find or whenever you fail to find tests or acceptance tests and unit tests that makes the unit under test fail. Okay, So here, each story is developed in a cycle that integrates unit tests in the inner feedback loop, as we have already discussed, and an acceptance test that is represented by the outer feedback loops. This is a simple elaboration of vertical integration testing. So it's basically unit testing plus acceptance testing in general, and the whole system, which is subject to vertical integration, is dissected or splitted by using the various user stories that you have got during the requirement specification phase. So just to recall what we have been discussing so far, we started by discussing the logical organization of testing. We discussed the different unit testing approach, and recently we have discussed about the integration testing approach. Now let's see what system testing is. So the goal of system testing is generally to test the whole system. In our specific case, for instance, the self-home access could be taken. So the goal of the system testing is to test the whole system in general. So for that, for instance, in the case of self-home access, we need to have oracles like locksmiths, electrician to undergo system testing. So system testing is more to the oracle based testing or the domain expert based testing technique. So in this scenario, for instance, we should have locksmiths, we should have electricians to check that the lock and electrical wiring are properly working. Or we could also uh, invite third-party software developers if we have used third-party softwares, for instance, for the locking digitization purpose. Another important system testing scenario that I can discuss with you now is the security honeypots. So basically, in the realm of cybersecurity, honeypots are entities that are built to deceive hackers or attackers. So this honeypot technique or security honeypot technique is basically a way to build a replica of your existing system, but feed it with or fill it with fake data so that the attacker, specifically the black hat um, hackers, will be deceived and assumes it's a real system and implements their hacking techniques on those fake data and replicated environments. So the benefit of this kind of type of platform or setting is that the people who are setting the honeypots will have a good access for the black hat hacker, specifically on the techniques applied by the black hat hacker to attack the real system. Okay, so there are two ends. To the black hat hacker end, the perception is that he's getting or she's getting the real system, but from the honeypot, you know, from the people who are setting or who set the honeypot system, uh, the system is generally a replica of the original system, but it's not the right system. So they are simply deceiving the attacker. So in the end or in the meantime, the attacker applies his attacking techniques, but the guys who are testing the attacker will know simply what kind of techniques will be applied by that attacker to attack the real system. That's all for this session, for this chapter. We have discussed about the different concepts regarding software testing. We started by defining software testing, and then we saw the different levels of testing, the different strategies of testing. We defined what unit testing is, integration testing is, system testing is. We also discussed about the varieties of system testing. The rest of concepts in this chapter are well articulated and discussed in our lab session. Next to this video lecture, I will be posting various hands-on exercises, and in that exercise session, I will be using Java for software testing. I will be using specifically JUnit and the different techniques that we can apply during object-oriented programming using Java. You will learn more about software testing and also, about Java as a software development language or a programming language in those consecutive sessions. But for now, it's enough. Thank you.